This Zoom session is being brought to you by the Fractal Crystal Ball. Okay, for today, we talk about the properties of functions. So various properties of functions. There's symmetries, even versus odd, increasing and decreasing, extreme values, and so on. Yes? Someone said something? Okay. Are we proceed?
Yes.
A question then. Yes? What? Well, never mind, we proceed. Okay, so here's the function, here's the graph of the function y equals x squared. Now, you can see that it's symmetrical left for right. If you flip it to the y-axis, you get the same graph. If x squared is on the graph, then negative x by x squared is also on the graph. That's true in general for a symmetrical left to right graph. If xy is on the graph, then negative x by y is also on the graph. For such a graph, for such a function. In this case, because negative x squared equals x squared, that applies. Here we have a graph of x equals y squared. It's symmetrical up to down. If we flip through the horizontal axis, you get the same graph. So y squared by y is on the graph means that y squared by negative y is also on the graph. Xy on the graph, x by negative y on the graph, we're symmetrical up to down. Now, this is not a function, however, because for a given value of x, which is y squared, there'll be two values of y. Here we have another non-graph, but it's a graph of a circle. And its graph is symmetrical around the origin. X squared equals y squared equals 1. If x by y is on the graph, then negative x by negative y is also on the graph. So, okay, and it's symmetrical by 180-degree rotation. Now, two of these are related to what are called even versus odd functions. An odd function is one which I like to say it transmits negative. F of negative x is negative f of x, so a negative comes outside. An example would be x to the third power, x to the fifth power, x to the seventh power, x to any odd power. So here's a graph of a function with this property. If x by y is on the graph, then negative x by negative y is on the graph. These graphs are symmetrical around the origin, like this. Now, this is not a function graph, but it is symmetrical around the origin. And any odd function its graph is symmetrical around the origin. And as you'll notice, it's these are functions of the form y equals x to an odd power, all of which are odd functions there for the name. An even function is one which absorbs a negative. So f of negative x equals f of x. So x to the second power, x to the fourth, or x to the sixth, or x to any even power is an even function. Okay, so obviously there's a symmetry between even and odd functions and even and odd powers of x. Okay, so if x by y is on the graph, then negative x by y is also on the graph. So therefore such graphs of such functions are left to right symmetric on the y-axis. Okay, increasing and decreasing functions. This function, the graph goes from lower left to upper right and never heads downwards. It's called an increasing function because when you increase the input, the output also increases. A less than b implies that f of a is less than f of b. So I actually prefer to call it order preserving. Here, this decreasing function goes from upper left to lower right. When you increase the output, you decrease the output. A less than b implies that f of a is greater than f of b. I prefer to call this order reversing. So here less than turns into less than, here less than turns into greater than. Here we have a graph which increases for a while, then decreases for a while, then increases for a while. It's increasing for x between negative pi and negative pi halves, also for x between pi halves and pi. And f is decreasing on the interval from minus pi halves to positive pi halves. Now, this thing increases for a while, then stops for a moment, then decreases for a while, and stops for a moment, and increases. So this point here is a local maximum. It's the biggest it is in its neighborhood. Here is a local minimum. F is the smallest it's going to be in that neighborhood. So, okay, local minimum is where f is the smallest value in its neighborhood, like this. And we write this down, minimum y equals f of a at x equals a. It's sort of important to note that it's minimum versus maximum, and note f of a, the value, and a, where it reaches that value. So these three things are required for an answer to this question. A local maximum is where f reaches the largest value in its neighborhood. So the maximum value of y is f of a at x equals a. A global minimum and a global maximum, these are where, not just in its neighborhood, but for all values of x. A global minimum is the smallest value of f anywhere. The global maximum of f is the largest value of f anywhere. So here's a graph. Here it reaches a global maximum, never any bigger. Here's a local minimum, smallest in its neighborhood. Here's a local maximum, largest in its neighborhood. And here's a global minimum, smallest in its neighborhood. A philosophical point. The philosopher Leibniz said that this is the best of all possible worlds, on the theory that God would never do anything worse. The satirist and rival philosopher, philosophers like to rival each other, Voltaire said, what? And he wrote a whole book titled Candide, consisting of a huge refutation of that thesis that this is the best of all possible worlds. He did this by putting his hapless protagonist through all sorts of terrible things, none of which would possibly be the best of all possible worlds. My view of the matter is that Leibniz knew the difference between a global maximum and a local maximum. And I think it entirely reasonable that this is the best of all sufficiently similar possible worlds, but there may be better possible worlds far dissimilar enough. Philosophy, never mind. Okay, so here are some examples. What is the symmetry of this graph? Well, it's symmetrical around the y-axis. What is the symmetry of this graph? This is symmetric around the origin. So in other words, if we flip this graph, it stays the same. If you rotate it around the origin, it stays the same. What symmetry has the graph of y equals absolute value of 2x? Well, f of x is absolute value of 2x, and f of negative x, twice negative x, the absolute value sign absorbs a negative. These are equal, so this f of x is an even function. Its graph is symmetric around the y-axis. What symmetry has the graph of xy equals 12? Well, you replace x by negative x and y by negative y, you get this, and this comes out to the same equation. So this is symmetrical around the origin. This graph, is this graph even, odd, or neither? F of x equals negative 3x cubed plus 2x. Well, what you do, you try to find f of negative x and see if it's either f of x or its opposite. The f of negative x is 3 times negative x cubed plus twice negative x. Negative, well, cube is an odd function, so the negative comes out. Here, x, it's just an odd function, it comes out. And minus and negative cancels to get 3x cubed minus 2x. This is not the same as minus 3x squared plus 2x, but it is the opposite of negative 3x squared plus 2x. So it's negative f of x. F of negative x is minus f of x, and therefore f is an odd function. Its graph is symmetrical around the origin. Here I have another function, x minus absolute value of x. Is it even, is it odd, or is it neither? Well, the idea is to find f of negative x. F of negative x is negative x minus absolute value of negative x. Here, the negative gets absorbed by the absolute sign, so you get minus x minus the absolute value of x. This is certainly not the same as f of x. And if you take negative f of x, you get negative x plus absolute value of x. So this is neither f of x nor f of negative x. So it is neither even nor odd. Here they ask if you can make any function even, and yes, the answer is yes. F of x plus f of negative x, all that divided by 2. The average of f and f of its of minus x. Prove that it's even. Well, the proof is simple. You look e of negative x, plug it in here and here. F of negative x plus f of minus f of minus negative f of x, all that divided by 2. Here the minuses cancel. You get f of negative x plus f of x over 2. But this is, up to commutativity of addition, is the same as this. So therefore, e of negative x is e of x. So e is an even function. Its graph is symmetrical around the y-axis. Here we have a graph of a function. Where is it increasing? Where is it decreasing? What's the local maximum, local minimum, global maximum, and global minimum? Okay, it increases up to here, and it increases from here to here, and from here to here. So it increases from minus infinity to -4, those values of x, and from minus 0.5 to 3, those values of x, and from 5 to infinity, those values of x. You look at the x values. Pay no attention to the y values, at least for this question. It's decreasing here and here. So x is going from -4 to -0.5, thus. And here x is going from 3 to 5, thus. Its local minimum is here. Y equals negative, oh dear. I have local minimum is here. Y is -1 at x equals 5. This is a global minimum. Y equals -3 at x equals -0.5. That you just saw with my cat's tail. Here, 3 by 1 is a local maximum. The local maximum is y equals 1 at x equals 3. Here is a global maximum. Y equals 4 at x equals -4. Okay, we have done what we need to do today. Oops, sorry.